Yes, if you have your quiz, go ahead and turn it in.
About the test.
Okay.
Would it be possible to take it on Friday? Like during class or something?
Yeah.
Okay. I just have a horse show and like a bunch of tests next week.
Yeah, if you want to take it Friday during the class, that's fine. I'll just set you up. Come to my office before class, like 9:45.
Okay.
And you can get started, and I'll just come down here.
Okay, thank you.
Yep. All right. Any leftover individual quizzes? Take-home quizzes. Any leftover take-home quizzes? Last call, take-home quizzes. So, our plan for today is to finish everything inhibitors, hopefully clear everything up, so we're all on the same page. Go through the serine protease mechanism as a good review. Individual quiz, then, looking ahead, we're going to look at Chapter 8. Just an overview of Chapter 8. Chapter 8 is everything about lipids and membranes, and we'll need that kind of information when we get a little bit later into the semester when we talk about the electron transport chain, the citric acid cycle, and why some proteins are membrane bound and some aren't. So this is just an overview of what does it mean to be a membrane, who are the players in making a membrane, things like that. And that was the suggested homework. And then to next week, Monday's exam 2, Wednesday no class, Friday chapter, let's see what comes next, 11. Good, everybody get on that? Yeah? All right, so I thought maybe the easiest way to clear up questions about enzymes and their inhibitors would be to solve it mathematically and to mathematically prove to yourself how does Vmax Km, Km apparent, and Vmax apparent change for each type of inhibitor. So we have a graph of each type of inhibitor that we're going to be concerned about. The issue is that for whatever reason various websites will not accept the EPTS. So it's stated as a P2F instead of virtually powerful. That was the issue. I didn't save it as a powerful. Your face is all right, so this top one should look familiar, all right, because that was on your quiz. That's the one you did, both in homework and on the quiz. Yeah, looks familiar. Good. So we're not going to solve this one because hopefully you've solved it at least twice, both with the same answer. Hopefully. So we'll just circle some important points on this, then we'll do the ones on the back. All right, so this one is my one with an inhibitor. And this one is my one without the inhibitor. A little hard to see. All right, so on which axis do I look for Km? The x-axis or the y-axis? I look for it on the x-axis. Does Km get calculated with an inhibitor or without inhibitor? Without. This one is Km. Because this one is the apparent Km, right? This is, I think, a big source of our confusion. Km is a constant all the time, considered for an enzyme with no inhibitor. When we add an inhibitor, it is no longer called Km, it's called Km apparent, because the actual Km is still over here, but your experiment's making it look like it's over here. So it's the apparent Km, because I had a question about this. If Km's a constant, why does it change? It doesn't change.
So why do we say that, like, with Ross on the quiz, or like, why do we have this whole thing saying that Km changes?
The apparent Km is different than the original Km. So it looks, experimentally, like Km has changed.
So, like, on the quiz, if we found that one, then it's still fine?
That's still fine. That is now called Km. I'm trying to make it more clear.
Okay.
That's called Km apparent. Because if you're doing the experiment and you didn't know if there is an inhibitor or not, you would say that's the Km. But in reality, it is the apparent Km. Yes, Sarah?
So when we say, like, increases or increases, it's really saying the apparent is less than the actual?
Yes. That is what you're comparing it to.
So you shouldn't say Km increases or decreases, you should say Km.
That would be more appropriate. Yep, and hopefully less confusing.
Okay.
Does that make more sense? Km is a constant for any one enzyme substrate combination. If it's changed, it's because it looks like it has changed based on the graph. Because there's an inhibitor in there competing, in this case, for it. Better? Better? Okay. So then, where do I look for my Vmax on the X or Y? Y. And if you solve this mathematically on your quiz, you would see that the Vmaxes are not the exact same number, right? They were close. They were close to each other. So it means that the real Vmax is approximately equal to the apparent Vmax. So when we say Vmax has not changed, we're really saying the apparent Vmax is almost the same as the actual Vmax for the experiment. The y-axis point has not changed. Does that make more sense? Better, better, better? Okay. I'm assuming blank stares means everybody's totally got it. We're ready for the next one. Okay. Let's work through then. What sort of graph is this one? We already did competitive. Which one is this one? There's really three choices. Uncompetitive. All right, so this one's an uncompetitive graph.
No. uncompetitive is not the same thing as non-competitive.
Correct, those are two different things.
Yep.
Yes, different. I don't know why they named it that way, competitive, uncompetitive, non-competitive, because un and non really mean the same thing, but they don't. Non means mixed. I don't know why they, ridiculous. When I get around to those biochemists who name all those things, I'll tell them a thing or two. All right, so let's look at this graph. For this graph, we want to determine Km, Km apparent, Vmax, Vmax apparent, and then we'll take a look at figuring out Ki. So, we said that the Km is on the x-axis. Which color, the green or the red, tells me regular old Km? It's a little hard to tell. No inhibitor is green, with inhibitor is red. I guess these aren't showing us real well. Green. So Km is calculated from Did I color them backwards? I did. I'm sorry. My squares must. Yeah, we'll make this. All right, that one's now green. Yeah, it's a little hard to tell on my graph. Sorry, I tried to print them off in color, but then we don't have a color copier. So if anyone wants to make a generous donation to Berry College for a color copier, really much appreciated. A big donation. If you guys all pitched in like $5. Apparently $42,000 is not enough for me to get a color copier. Sorry. $42,000 each. We need $5 on top of that. All right. So now I got my color coding, right? It's a little crazy looking. It's all right. You just need the equation on the line. All right. So I want to calculate Km for no inhibitor. So how do I go about using my equation on the line? How do I go about setting this so that I can solve for Km? Make the y 0, because I'm looking for the x-intercept. That's what that turns out to be. Should be about 1, right? So am I done? No, what do I need to do to actually get to Km? That's my little negative sign. And looking at the graph, is that your x-intercept is reasonable based on your graph, right? Your x-intercept should be about 1. You calculate it to be about 1. Okay, good. So then, I want to find the Km apparent. So I use the other equation. And do the same thing. Hopefully someone's checked my math out there. Should be right. Which one should be negative? What? All right, I'm assuming silence means it's okay. So I have my Km, which was 1. My Km apparent is 0.37. What has happened to my Km value? Decreased. Good. Good. It should decrease. For an uncompetitive, Km should decrease. All right, let's take a look then at Vmax and Vmax apparent. Use the same equation.
Does KM not have units or
It does have units.
to use the ones on the x-axis?
Use the ones on the x-axis. So what would be the units of Km for this particular graph? Millimolar. Good. All right, so now I want to find Vmax. How do I mathematically solve for Vmax? If it's the y-intercept, what thing do I set to 0? Set the x to 0. Yeah. Mathematically, that'd be true. So am I done? Or how do I get to Vmax from there? I gotta inverse it. Okay, so based on what you know about uncompetitive graphs, what do we expect to happen to the Vmax apparent value? To be greater or smaller? Should be smaller. So we're going to mathematically see if that's true. And its units are, for whatever, I don't know what the OD is symbolizing on the graph, but it's OD per minute for Vmax. Must be referring to something in the problem. All right, so did we prove what we think should happen with our Vmax? Good. So then the last part is to figure out Ki. All right, so the problem was, all right, just like you had in your homework, I have to figure out what the inhibitor concentration is out here. All right, so the equation for alpha is alpha equals 1 plus concentration of I over concentration, or over the inhibitor equilibrium constant. So the first thing we have to do, we have to figure alpha. All right, because otherwise there's too many things that we don't know. So to determine alpha, alpha is the ratio of Km apparent to Km. So it's by how much did the Km value change? So it was at 1.01, it's now at 0.370. So we're figuring out by what, how many factors did it change by? It should be about 3. .3. Most people got this in their homework, so not too worried. So then, what's the other piece of information I need to give you in order to be able to solve it? Concentration. So the book concentration is 0.022 millimolar. So then we plug that in. And that cannot be right. Let's see if I'm reading off the right problem. I know what went wrong. I got these reversed. Right, alpha value is, it's 1 if it's inhibiting, it can't be less than 1. So I got this flipped upside down. Should be 1.0.
Wait, why is it? It's supposed to be the KM over there?
Yep, that's what I got wrong. That makes more sense. Right, because alpha is 1 if there's no inhibitor, so I can't have an alpha value less than 1. That's not possible, which is why I was getting a crazy subtraction over here. There we go. That makes much more sense. Questions in solving that? If you compare the Ki to the Km for this particular one, Ki should be less, which it is, so that's good. Okay, then let's do the last one. Let's look at the mixed. All right, let's see if I can color this correctly this time. No inhibitor is the square, which should be this one. Yeah. So let's look at the same steps. I want to find Km apparent. So looking at the graph before we calculate anything, first of all, what kind of graph is this? Mixed, un, or competitive? It is mixed. How do you know it's mixed? It is technically the only one left. If you didn't know it was the only one left. The Vmax and the Km have both shifted. So we would expect both the K, so if you're thinking about it logically, like competitive only changes Km. The uncompetitive, the slopes are constant. This one, it is kind of a mix of both un and competitive. That the slopes have shifted so that Vmax and the Km have both moved around. That helps you think about.
How do you tell the difference between mix and the?
Non?
Yes.
You cannot assume for this class that they are pretty much the same thing.
Okay.
They have the same rules.
Okay.
So really, we're going to consider 3 classes: competitive, uncompetitive, mixed. That should hopefully make it. Mixed is really non, but those be those three areas. All right, so use our equation in the graph. No inhibitor. Okay, so if that's the x-intercept, what do I need to do to get to the Km value for that? Mm-hmm. Good thing to know, Km values are always positive. It helps you keep track of your negative signs. Km values are always a positive number. You have to do the negative. Okay, so then I want to find the Km apparent. About 2.02. All right, so what happened to my Km in this case? The Km increased. Mm-hmm. So the apparent Km increased. Let's see what happens to the Vmax. Anyone have a guess off the top of their head what's going to happen to the Vmax? It should decrease. Yes, so let's take a look. All right, how do we feel about that? we feel more confident in our inhibitors now? So like worst case scenario, you don't identify it without looking at it. You should be able to identify it without getting too confused, right? There's only 3 types of graphs. But worst case scenario, you don't recognize what kind of graph I've given you. You should be able to calculate and then figure out, oh, what happened to the Km? Because, you know, in the mixed, it's a little tricky to tell exactly what's going on with the Km because the points come real close to each other. So you should be able to calculate it, tell me what happened to the Km, calculate what happened to the Vmax, be able to tell me if it's which one of the 3 it is. Yeah, Katie.
On our like little sheet that we got,
Mhm.
it mentioned with like the non-competitive or the mix that Km could increase or decrease.
Yes.
Are we like on this one it increase?
Yes.
So we always gonna see an increase, or is it possible that we could calculate and a decrease? So we'd have to calculate Vmax.
It is possible, yeah, it's possible for Km to increase, but you should be able to recognize it from the graph anyway. If the Vmax has the Vmax intercept, like where the 2 Vmaxes cross, if it's not on the y-intercept, then you know for sure it's mixed. If I ask you specifically, like, how is the Km changing, then you have to calculate that part of it. That should be pretty straightforward. Questions on any of that? How are we feeling?
So you can just like, the mixed one, the Vmax is always going to decrease,
Yes,
but the Km can like decrease or
correct. Yep. And it's going to depend on the slope of the inhibitor, right? In this case,
Yeah.
it's kind of slopey, but if you could imagine it slopes a ton and now it intersects all the way down here, right? Or maybe it doesn't slope very much at all and it's more like that.
yeah.
If it does that, then the Kms are about the same. It could do something crazy like that, and then the Km would be less.
Yeah.
So, yeah. Any other last lingering questions about inhibitors? All right, in that case, let's do the serine protease mechanism again. Walk our way through that. You can either sketch it again or you can just follow along your notes. Either one's fine. All right, anyone have a good guess as to what this amino acid is? If you see the R group, definitely histidine. What about this one that has the alcohol as its R group? Serine. This one that has the carboxylic acid as its R group. Aspartate. If you don't remember your amino acids off the top of your head, you may want to go back and review them because they'll come up again a lot over and over again. Just saying. All right, so we're going to have our little peptide enter our active site. All right, there's our amino acid. What bond is this one right here? Oh, I heard peptide. It's the peptide bond. That's the one. We are looking to break our peptide bond. So that's the serine protease. Its main function is to break a peptide bond. So write that down someplace. Breaks peptide bonds. It does that in 5 steps. So step 1 is having, let me back up. Is serine an amazing nucleophile in its current state as an alcohol? No, pretty sucky actually. It would be a terrible nucleophile. Luckily, we have this histidine right next to it. I draw the H on the wrong side. So that nitrogen with its lone pair is going to grab that proton off of serine. What charge would serine have then once its proton is removed?
Is the air coming from the nitrogen?
Technically the lone pair on the nitrogen. Yep. All right, so it's going to have a negative charge when we are done with it. Is that a good or bad nucleophile? An oxygen with a full-on negative charge. It is an amazing nucleophile. It is ready to do some chemistry. So it is going to attack that carbon and push the electrons up onto the oxygen. So in this case, what kind of catalyst is histidine acting as? It is a base catalyst. Also good to know. In this case right here, histidine is acting like a base catalyst because it's grabbing a proton for itself. Histidine is acting like a base catalyst. Yep.
I remember my notes did act like
It can go either way.
Oh.
And it will act like an acid catalyst in about 2 steps.
Oh.
So this step, base catalyst. How is serine acting? Acid, base, redox, or covalent? It is a covalent catalyst. How do you know it's a covalent catalyst? It is making a new bond. It's making a bond between the oxygen and that carbon. So new bond, covalent catalyst. All right, step 2. All right, so we've made our new bond on serine. At this point, we're going to make a tertiary intermediate. Tertiary intermediate. And we're going to do this with this full-on negative charge. It's going to collapse onto that carbon. So now it's ready to push those electrons someplace else. That bond's going to break, so our peptide bond at this point has now broken. So the nitrogen needs another proton before it can float away. It's going to grab that proton and push the electrons back onto the nitrogen. Okay, so that's step 1, that's step 2, step 3 is over here. All right, so now step 3 right here. Our NH2R2 group has left the active site because we just broke that peptide bond. Now NH2R2 floats away. I'm going to add some water to my active site because I have to regenerate my active site to what it used to look like. So really, the activities in these first 2 steps, The next 3 steps are just regenerating the active site to the spot, to what it used to look like. All right, so there, my water has now entered the active site. What you're trying to do is you need to cleave this little fragment off, because that's messing up with your active site. So this oxygen is going to enter the active site and donate a proton to histidine. Oh, sorry, I drew it on there too early. That should be in lone pair. So no H there yet, sorry. Lone pair. So water enters, donates a proton to histidine. The remaining hydroxyl group attacks the serine. So step 4, we'll look at the rest of the chemistry that's going to go on. So the hydroxyl group has now attached to the carbon. We have a full-on negative charge on that oxygen. We're going to go through another tertiary intermediate. Looks pretty much just like this one that's directly above it. So pretty much you do a base catalysis, tertiary intermediate, acid catalysis, no, sorry, base again. No, base. Base catalysis, acid catalysis, tertiary intermediate. This, that. So you lose that other fragment, and you're back to your original active site. So pretty much you just do the same steps twice through. Yeah.
What is aspartate?
Its job throughout the whole thing is to really hang on to the proton over here on this side of histidine. Because in theory, once we get to this step, both nitrogens look the same. And if this one grabbed this proton over here, the chemistry wouldn't be correct. And so its job is to keep that proton from leaving, so that this one's even more favorable to leave. Yeah.
Where did the hydrogen come from in step 4, attached to the nitrogen?
From here?
Okay.
That
so
nitrogen-
the other one,
yeah.
hydrogen just went there.
Right, so the water broke up. One nitrogen went here, and then this is the rest of the water.
Okay.
So that guy and that guy were water. All right, how about we take a quick individual quiz? Ooh, question first while I pass these out.
In the notes, you talked about the tetrahedral.
Yep,
Is that just 72?
that should say tetrahedral, what does it say?
Is that like where it,
It's where, like in organic chemistry, it makes actually kind of a square.
Like the geometry.
Like the geometry is a square, so it's here. Geometry is a square.
and the carbon and then
And then for sure you guys talked about it. That when you get to a tetrahedral intermediate, it definitely goes forward.
I'm dropping everything.
That's right, one of those.